Noise is like a raging fire. In its wild, untamed form, it has the power to spread destruction. Yet like fire, if we harness its power, noise can become an instrument of creation. I remember a time when the thought of deliberately shattering perfect shapes left me puzzled. But then, a revelation struck me. Nature had been doing this all along. This sent me down a rabbit hole, a journey into the beautiful complexity of noise. And now, I invite you to join me on this journey. By the end, you'll comprehend the dynamic interplay between noise and nature. You'll learn how to create noise using simple algorithms and even put it to good use. But most importantly, I want to inspire you to appreciate the art of procedural noise. In our exploration of noise, there is a cornerstone we must understand first: randomness. It is randomness that gives noise its raw and chaotic nature. Picture this. You're trying to decide who gets the last slice of pizza, and you flip a coin. Heads, it's yours. Tails, your friend gets it. But is the coin flip genuinely random? Technically, if we knew every precise detail of the flip, the coin's initial position, the flip's strength, air resistance, and more, you might be able to predict outcome with almost perfect accuracy. Does that make the coin flip genuinely random then? For that matter, does true randomness even exist? To escape the domain of philosophy, let's call something random if we cannot predict its outcome perfectly based on the available information. By that definition, it is safe to say that coin flips really are random, at least for all practical purposes. Randomness is present all around us, and it manifests in myriad beautiful ways besides just simple coin flips. For instance, let's think about a bit of ancient technology, the radio. Tune in to an empty station and listen. The signal doesn't make any sense. Graphing the signal as a function of time, it seems like we get a random value at each point in time. Such functions are so common in our universe that we have a special name for them. We call them noises. Noises are by no means limited to one-dimensional signals. For instance, every digital photograph is damaged by noise. Instead of getting an image corresponding to the light that landed on the sensor, you get that plus some random value added to each pixel. This kind of noise seems destructive, but not all noises are like that. In computer graphics, we use noises to create things, not to destroy them. Using noise, you can for instance create a realistic mountain range really quickly. As we delve deeper into this video, we'll explore many types of noise, each with its own unique characteristics. Despite their differences, there's one trait they all share, and that's their unpredictable, random nature which they bring to the table. Now, you may wonder, how do we obtain noise in practice? There are two main ways we can get our hands on noise. The first method is straightforward. We measure the noise we observe in the real world. For instance, we might measure the audio signal from the empty radio channel, giving us a noise function. The second way is more tricky. We can generate noise by giving the computer step-by-step instructions on how to create it. The noise made this way is called procedural. The buzzword procedural is popular nowadays, especially in computer graphics and game development circles. The core idea is to design an algorithm to generate something for you. For instance, you can create an algorithm that will generate a texture for you instead of taking a real-life photo and editing it. To begin, let's walk the fine line between these two strategies. We'll use a coin flip to generate noise. Don't be deceived by its simplicity. Even a humble coin flip can create complex noise. If you got a pen, paper, and a coin lying around, you can follow along and create a noise of your own. Pause the video, grab those items, and let's get to it. First, just pick a spot in the middle of your paper. Then flip your coin twice and jot down what you get. Should you flip 2 heads, draw a line upward. For 2 tails, draw downward. If the flip results in head and then tail, move to the right. If a tail followed by head occurs, go left. Each time you draw a line, use the ending point as your new starting position. You can attempt this experiment several times. You'll see that each iteration almost always yields a unique outcome. You can explore this idea even further. We have only used 4 directions, but with a dice roll you get 6. With 3 coin flips you get 8. You can even introduce some variability to the line lengths. Go ahead and have fun with this noise. By the way, I have said that this noise is a blend of procedural and non-procedural noise. Can you see why? We followed a specific procedure, so it might seem like a procedural generation. But the randomness came from real-life measurements of coin flips. As we progress, we'll learn how to remove the physical coin flip from the equation and generate noise truly procedurally. But before we jump into that, let's consider a real-world process that exhibits a similar form of randomness to our coin flipping experiment. Believe it or not, a drop of dye dispersing in a glass of water is linked to our coin flipping noise. When we zoom in, and I mean way in, we'll see countless particles in the water darting in random directions. This microscopic dance of particles is known as Brownian motion, named after the scientist who first studied it. And it is this very motion that causes the dye to disperse evenly in the water over time. Now let's pick a single dye particle and track its journey. It gets knocked around continuously, each collision setting it off in a different direction, producing a really intricate path. We call this path Brownian noise, named so due to its origin in Brownian motion. Can you see the similarities to the noise we generated by flipping a coin? Besides being intriguing, Brownian noise is also highly useful. Let's see how we can employ Brownian noise to create something truly remarkable. We can start with a 3D cylinder and few lines on top of it. By applying our Brownian noise, we can distort the shape of these lines to achieve more interesting forms. Now, using an extrusion tool, we can transform them into cutting surfaces. With these, we can slice our geometry into pieces and produce a beautifully fractured terrain. Speaking of terrain, it is rarely flat. Consider the towering peak of Mount Everest at an elevation close to 9,000 meters, or the majestic Mount Fuji, stretching just below 3,800 meters. These are specific points, but what if we could have a function that, given the coordinates of any place on Earth, returns its elevation? Is it reasonable to view such function as a form of noise? Given the intricate interplay of various processes changing the terrain over eons, I would say interpreting it as a noise is quite reasonable. Let's break it down. Terrain formation occurs on multiple scales. A few things, like tectonic motion, can reshape the entire mountain ranges, although they take ages to occur. At a faster pace, erosion steadily changes landscapes, but on a smaller scale. Also, there are subtle but swift modifications made by living organisms. These diverse processes, each unfolding at their own pace and scale, contribute to the complex nature of our terrain. This poses an intriguing question. Could we use mathematical functions to mimic these processes at each scale and combine them to form a function that resembles the elevation? If we could, we would essentially have a tool to create noise. Let's simplify for a moment. Imagine taking a vertical slice of the terrain and viewing it as a one-dimensional function. For a while, we will limit ourselves to the ground scale created by processes like tectonic motion. To isolate this part of the function, we can simply smooth it out. From the graph, we can read out a few things. First, the function is definitely bounded. And second, it oscillates up and down repeatedly. To recreate the terrain from simpler functions, it seems reasonable to select functions that are oscillating and bounded, just like the terrain itself. Sine and cosine functions, or sinusoidal waves as we often call them, could be helpful here. If we slide, squeeze, and stack a few of them, they might start looking like our smooth out terrain. But to bend them to our will, we need to know more about how they work. The simplest sine wave is sine of x, which goes through one complete cycle over a distance of 2 pi. We call this distance the wave's period. The wave's frequency is the number of complete cycles it makes in a certain span. Usually, we talk about the frequency over a span of 0 to 2 pi, where our basic wave, sine of x, makes exactly one cycle. We can speed up or slow down this cycle by multiplying the input by a number b. This changes the period to 2 pi divided by b and the frequency to b. We can also shift the wave left or right by adding a number c to the input. In this context, c is called phase shift. We'll stick to phase shifts between 0 and 2 pi because shifting in more than that just loops it back to where it started. Finally, we can stretch or squash the wave vertically by multiplying the whole function by a number a. In this context, we call a the amplitude of the function. With these three variables, we can whip out all kinds of different sinusoidal waves. We're going to be working with a lot of these waves, so instead of messing with numbers every time, let's just use a picture to help us out. Here's how it will work. The horizontal axis of our graph shows frequencies getting higher to the right. Points below the axis show the phase shift of a wave. And points above the axis show its amplitude. The farther a point is from the axis, the bigger its value. Now that we've got a better understanding of waves, let's see if we can combine them to create something that looks like the slice of terrain. Let's start by adding waves of different frequencies, but keeping the amplitudes and shifts the same. As we add more waves, things begin to get more complex. However, we run into a problem. The output gets really big really fast. So how about we tame this growth by dividing the amplitude of each wave by the total number of waves we're using. This keeps things from getting too big, no matter how many waves we add. But when you look at the output, it doesn't really have the noise-like quality we're after. We have already played around with changing the amplitude, so what if we tried mixing up the phase? What if we gave each wave a random phase? It is interesting to see how just a small change like this can have such a big effect. But we can do even better. Let's think back to when we were discussing how terrain is formed. We've talked about how big, broad changes have significant impact, while smaller changes tend to be less impactful. What if we use this idea in our wave generator? Right now, all our waves have the same amplitude, but what if we gave more weight to lower frequency waves and less to the higher frequency ones? Now that's looking more like the kind of noise we want. To make things even more interesting, let's try adding some randomness to the amplitudes. We can do this by multiplying the amplitude of each wave by a random number between 0 and 1. Now you are getting some really interesting noise. If we look closely, we can see a lot of detail at many different scales. Feel free to play around with this technique and make it your own. By experimenting with different ways to scale the amplitudes, you can create all sorts of different types of noise. This brings up an exciting question. Can we make any kind of noise just by adding together simple waves? As it turns out, the answer is yes. Imagine we have a noise function that only operates between 0 and 2 pi. With a few mathematical tricks, we can break it down into a bunch of simple wave functions. When you add all these waves together, they perfectly recreate our original noise function. What's really cool is that the function doesn't even have to be noise. We can take almost any reasonable function that works within the same domain, break it down into simple waves, and when we add them all back together, we get our original function back. The nuts and bolts of how this breakdown happens are interesting, but unfortunately, we don't have the time to get into it here. I'll leave you with some resources to look into it on your own. For now, we'll just use this approach as a different way to understand function. When you study a function by looking at its graph, we usually say that you're looking at it in the spatial domain. But when we start to think about the function as a group of waves, we say that we're looking at it in the frequency domain. Frequency domain viewpoint can offer us some extra insights. Let's compare our noise made from summing up waves and the mountain noise side by side. If we look at them in the spatial domain, they look similar. But that's not saying too much, since it is only our subjective view. For all we know, the two graphs might have only a few points that share the same value, or they might not even have any such point. That's where the frequency domain steps in. When you look at the frequency domain of both noises, we can say a few things about them. Both functions have similarly distributed amplitudes, which play an important role in their similar appearance. Second, both functions have seemingly random phases, but the mountain noise isn't as uniformly distributed over the entire 0 to 2 pi interval. Our generated noise isn't exactly the same as terrain noise, because the process of terrain formation has some specific characteristics that make the noise behave in a certain way. That being said, let's return to the idea of noise in the frequency domain. Let me introduce you to a very important type of noise, white noise. You are pretty familiar with what noise is by now, but what about the white part? Just like noise, light can also be seen as a sum of waves that stretch across a range of frequencies. When all frequencies in an array of light are evenly spread out, we see the light as white. The idea behind white noise is pretty much the same. We call noise white if all its frequencies are evenly spread out. It would take a lot more math to define white noise properly, so for now, I'll just show you an approximation of it. Let's add up a bunch of different waves again. This time, we'll pick frequencies that keep increasing. Each amplitude will be a random number between 0 and 1, divided by the number of waves. And the phase will be totally random. The more waves we add, the closer we get to white noise. Notice that the more waves we use, the faster the function changes. True white noise changes infinitely often. Here's something interesting. Our noise-making strategy is just a simple transformation of this white noise approximation. By manipulating the amplitudes of this white noise approximation, we have essentially tamed it into the same kind of noise we have created previously. This manipulation of amplitudes is, in fact, a special case of more general idea called frequency filtering. The main idea behind frequency filtering is to tweak the amplitudes of different waves in the frequency domain. More often than not, we use one of the three basic filter types. We have already came across a low-pass filter. As you can guess from the name, a low-pass filter lets low frequencies through while it tones down the high frequencies. This has the effect of blurring the function, which is pretty much what we did when we created our noise. The opposite of a low-pass filter is a high-pass filter. This type of filter cuts out low frequencies and keeps the high ones. The result? It gets rid of the big shapes in the function and only keeps the tiny details. You can also use a combo of the two filter types, which we call a band-pass filter. This lets you cut both high and low frequencies, keeping only the frequencies within a certain range. Besides these basic filter types, you can come up with many other filters. Feel free to play around with this on your own. Now, let's flip the page and see just how well our noisemaking strategy works. We know our algorithm can create some genuinely nice results. But there's a problem. It's not exactly efficient. What do I mean by not exactly efficient? Let's take a closer look. Remember, we have set up the noise generator to add sine waves. Let's say we are using 100 waves. To figure out the noise at specific point, we have to calculate the sine 100 times and add all these calculations together. You might need to add thousands of sine waves if you want more complex noise. That's a lot of work to get just one value. When you use noise for practical purposes, we often need to evaluate it for many inputs. This means the inefficiency can really add up. Say you're creating a 3D graphics and use noise in a texture. The render engine will compute the noise millions of times. If your noise algorithm is slow, this could turn rendering times from minutes to hours. Therefore, making the noise algorithm efficient is one of our main goals. Besides the inefficiency problem, we still need to address one more thing. We need to generate sequences of random numbers. Unfortunately, throwing a dice whenever we need to use noise isn't feasible. Let's start by figuring out efficient ways to produce random numbers. One possible way to obtain random numbers is to use some real-world noise. Say, with our terrain slice function, we could sample at set intervals and consider these numbers as random. However, gathering and refining this data is a hassle, not to mention the storage demands. Fortunately, we have a more efficient method that does not depend on real-world data. The idea is to let a computer generate random numbers. Generating random numbers on a computer seems straightforward, but there is a catch. Computers are built to execute instructions with predetermined outcomes. To address this, mathematicians invented a clever solution, the pseudo-random number generator. It can create sequences of numbers that seem random but are actually predetermined. A pseudo-random number generator works by starting with a seed number. This seed initiates the generator. Then you can ask the generator to give you a random number. We will use a generator that comes up with a random number based on an integer index. For example, it can generate 10 numbers based on indexes from 1 to 10. There is a limitation though. This algorithm isn't truly random, and after a while, it will begin to repeat, hence the term pseudo-random. However, for our procedural noise generation needs, this is typically acceptable if we're mindful of the constraints. There are countless ways to create such generators. One of my favorite methods will be the topic of our next section. We are going to use a hash function. A hash function is a function that takes in a key, which can be almost anything, like a string or an integer, and converts it into a hash value. It has a specifically defined set of hash values it can output. The thing that makes hash functions interesting for us is that a good hash function evenly spreads out its hash values for most input sequences. To demonstrate this, let's consider a hash function that outputs 10 different hash values. If we take a sequence of 4 integers and get a hash value for each one, the result should be a sequence of 4 hash values that seem to be randomly picked from the 10 possible ones. With this, we can quite easily generate random numbers. We simply assign numbers to each hash value. To the first hash, we will assign 0, the second 1 divided by 9, and so on. This way we can convert sequences of integers into sequences of numbers between 0 and 1 that seem to be randomly picked. Most hash functions are flexible enough and you can give them a seed to alter their behavior. If you want more possible random numbers than 10, you can simply pick a hash function with more hashes. Now you're probably asking, how do I make a hash function? I'm sorry, but I will leave that one for you to figure out. You can start with the resources in the description. For now, let's finally discover an efficient way to generate noise. Let's return to the noise generated by summing up waves for a moment. That's our benchmark for the noise we want to create more efficiently. But this time, instead of focusing on frequency domain, let's look at the noise in the spatial domain. We can pick a few points, spaced evenly apart, and observe the noise values at these points. When these points are close together, the subsequent values are often quite similar. A high value in one sample typically means the following sample will be also high. However, this dependence diminishes as we increase the distance between the points. Once the points are far apart, our samples look like random values. What if we try to connect these points with straight lines? This gives us a function that looks like a terrible approximation of the original noise. But that's fine, let's try to refine it. The way we have connected the points is called linear interpolation. The main idea of interpolation is to compute missing data points. In our case, we did it with lines, but we could also use different functions to calculate the missing points. For instance, cubic polynomials, which can give us a much smoother result. Unsurprisingly, this is called cubic interpolation. Since our end goal is to generate noise and not to approximate existing noise, let's take a step forward and replace our sampled points with random values. We can assign a random number to each point in the sequence using our hash function method. We will use numbers between -1 and 1 instead of 0 and 1. The points to which we've assigned random numbers are called not points. This is already a noise function, just one that is very smooth. In computer graphics jargon, we call it the value noise, and it is one of the simplest and most efficient ways to generate noise. Let's look at the frequency domain of the value noise to see how we can improve it. At first glance, we did a good job of creating a function that behaves like the reference noise in low frequencies. But the problem is that it completely lacks the higher frequencies. Therefore, our next step is to figure out a way how to add high frequencies to the value noise. Similar to sinusoidal waves, we often talk about the frequency and amplitude of noise. The value noise function we have defined ranges from -1 to 1, which gives it an amplitude of 1. We define its frequency as 1 divided by the distance between not points. Therefore, our value noise has a frequency of 1. Like with sinusoidal waves, we can change its amplitude by multiplying the entire noise function by A. And its frequency by multiplying its input by B. Now let's try to add up two noises with different properties. To keep the resulting function at reasonable scale, like with sinusoidal waves, we want the sum of amplitudes to be 1. As with sine waves, we can achieve more complex results by summing more of them. So let's develop a strategy for summing these waves. For instance, we could double the frequency and halve the amplitude each time. Summing up 5 noises like this, the results gets incredibly complex. However, there is a minor issue: the function grows too much, because the sum of all amplitudes isn't 1. This can be easily solved by dividing the resulting function by the sum of all amplitudes. We have quite arbitrarily decided to multiply frequencies by 2 and divide amplitudes by 2. This is just a special case of fractal Brownian motion, in short FBM, a method for creating fractals by summing up self-similar patterns at different scales. Instead of 2, we could use a parameter, which in FBM is called lacunarity, a Latin word for gap. And instead of halving amplitudes, we could use a parameter called roughness. With higher values, it indeed makes the result appear more rough. The number of sound waves can be set using a parameter called octaves, a term borrowed from music theory, often used to describe the number of scales in a fractal. Looking at the frequency domain of the noise, we can confidently say that we have managed to add high frequencies. The reward we get is the noise with an arbitrary level of detail. We have touched on some key concepts of noise generation, going from noise in the nature through creating noise in the frequency domain to the beautiful fractal noise. However, this is only the peak of the iceberg, and there is much more to explore. If you want to learn more, let me know in the comments below. I might create a follow-up episode. In the meantime, you can check my video on math for procedural texturing, which might help you implement what we've covered today in practice.